This video is about writing a Bellman equation. So if there is a problem given like this, where a consumer has the following problem, maximize summation t equals 0 to infinity beta to the power of t ln, meaning natural log of c sub t, where beta is between 0 and 1, subject to the budget constraint or subject to the resource constraint, x sub t minus c sub t equals x sub t plus 1, where xt is given. And these variables are defined as follows. C sub t is consumption at period t. X sub t is the resource given at period t. X sub t plus 1 is the resource available at period t plus 1. So we we can easily see that the variable that is given is xt, the resource that is available at period t. This is the state variable, the variable that is given at the initial state. That is called the state variable. And the control variable is the variable which is also called the choice variable that the consumer chooses to maximize his or her utility. So in this case, the utility function is ln of ct, c sub t, log natural log of c sub t. So now if we want to write this Bellman equation, we have to consider these two variables. The state variable, the Bellman equation expresses the value as a function of the state variable at time t. So value of the x variable at time t is v of x sub t is equal to the utility of the consumer, which is here ln of c sub t, plus the discount factor that we have here, so beta times the value function at t plus 1. So the value function in this time at t plus 1 will be value v of x sub t plus 1. X sub t plus 1, the state variable at t plus 1, subject to the resource constraint x sub t minus c sub t, which is equal to x sub t plus 1, where xt is given. So we can see that if we have an infinitely lived agent, uh, the agent lives from 0 to infinity, and the utility function of the agent is this you can also call this the lifetime utility of the agent, which runs from 0 to infinity. And of course, the agent discounts the future period consumption by certain discount factor, which is b, which is beta. So that's why we have here beta to the power of t, and ln ct, and the consumer has to consider the initial resource that the consumer sees. For example, the consumer may have some resource that is limited. Okay, say xt. For example, it might be some water in the reservoir. So if the consumer consume at period t ct, at the beginning period xt, the consumer takes out ct uh, of the water, then if there is anything left, that will be xt plus 1, meaning the water available in period t plus 1 will be x sub t plus 1. So the Bellman equation breaks this problem into a two-period problem. T period problem at a t value and a t plus 1 value. So that the value at t is v of xt, which is equal to the current period maximization of utility, and whatever is remaining is v of x t plus 1, because x t plus 1 is the available resource at period t plus 1. And because the consumer discounts the future consumption by a factor of beta, so we have this beta here. And of course, the budget constraints, we need to put the budget constraint here too. If we look at this, the original problem, we see that in the Bellman equation, we don't have the beta to the power of uh, t, because beta here in this case is beta is the t is 1, and so that's why we have only. And in the current period t, the value of t is 0 because there is no discounting, so that's why we only have this ln of ct. So I think that explains how we can write a Bellman equation from a infinitely lived agent. It can be done for any finitely period lived agent too. So this is a discrete time problem. Bellman equation is a discrete time dynamic optimization problem. It is called uh, recursive because it depends on for example, the value function in future depends on the value function at now, or we can also say the value function of today will depend on the value function of tomorrow. So it calls itself, the value function calls itself. That's why it is called a recursive uh, function. The Bellman equation is a recursive function. All right. So again, the value function has two parts. One is the current period optimization of utility, or if it's cost, then it would be some cost function here, and then a value for the next period discounted by some discounting factor. Okay. Okay. So that's how we can write a Bellman equation given a given an optimization problem subject to a dynamic optimization problem, of course, subject to some resource constraint. Okay, thank you.